Hello everyone, nice to see you here in MedComNet 2020. I'm Zhang from Politecnico di Milano. This work was done in cooperation with Francesco Devoti and Professor Filippini, who is my supervisor. Glad to share our work RL-based resource allocation in mmWave 5G IAB networks. Since the webcam window blocks the content, we close it from here. Okay. As we know, 5G networks involve millimeter wave as a solution to the mobile traffic growth, which allows us to reach a high frequency so that we can use huge untapped spectrum resources. However, it suffers from high path loss and obstacles, which can be alleviated by directional antennas. Another con is the coverage-limited deployment that can be tackled by installing BS densely, exploiting the IAB architecture. IAB is an acronym for Integrated Access and Backhaul. IAB network is a typical self-backhauling network with multi-hop architectures where access and backhaul transmissions are carried out in the same frequency band. It includes donor, IAB relay nodes, and the users. Here we present a typical routing and scheduling problem in IAB networks. We can see that in this small network, the classical optimization methods provide us with a solution where two different patterns in different slots carry data from this donor to these two users. But now we have obstacles on this link, so the current solution is not valid. If we repeat the optimization procedures from the very beginning, it will take a lot of time. So now our idea is to use the adaptability of RL to find a new best routing and scheduling easily. And our current solution should be this one. We can see that the first pattern is replaced by the third pattern to let the data bypass the blockages instead of being affected and transferring nothing. Here's a summary of our work. In all, we apply RL to solve the problem of flow allocation and link scheduling to maximize the throughput in a multi-hop IAB architecture. So we jointly coordinate access and backhaul, and we put emphasis on more realistic environments and on reliable networks that can encounter dynamic and complicated blockages, and we provide both offline and online versions of the approach. In this talk, we first have a general idea on the system model and deep reinforcement learning. Then we introduce the approach proposed in three aspects: CG-based scheduling patterns generation, buckets pipes game, and how to play this game with RL. We show the experimental results and draw the conclusions finally. Before unfolding the approach, we first introduce network scenarios, link patterns, and blockages. This picture shows us a typical scenario. It arranges donor, IAB nodes, and end users in a multi-hop topology. Donor reaches users directly or via multi-hops, including backhaul and access. We consider here scheduling approach, which enables several transmissions in parallel in a slot. These transmissions are supposed to meet the requirements like interference, half duplex, and so on. We call this set of simultaneous links pattern. This figure shows 5 possible patterns marked by different colors. The blockages we consider in this work are intermittently imposed on both backhaul and access slot by slot. That is to say, the links are blocked with a probability P. The environmental change means that the value of P is changed on some links. We first formulate the work as an optimization problem. Our aim is to maximize the total bits received by users per frame through flow allocation and link scheduling. At the same time, we're supposed to meet some constraints. Firstly, we need to ensure that we won't prefer users with good positions. Here, we use minimum data rate to guarantee this fairness. And we must ensure that the incoming traffic must equalize the outgoing traffic. And certainly, the traffic should not exceed the link capacity. Finally, there are some physical requirements that we consider in pattern generation, like interference, half-duplex, multi-beams, and power. After we have a general understanding of the problem, we introduced a little bit about deep reinforcement learning. Firstly, RL resorts to the interaction between the agent and the environment. The agent chooses the action based on the current state and the policy, and the environment transits to another state and gives a feedback to the agent. This is a typical Markov decision process, and RL's goal is to maximize the long-term reward, which is represented as return. RL methods are sorted into two categories, that is, value-based and policy gradient. The so-called value here is generally the expected return. For value-based, the agent chooses the action with the largest value at the current state, and for the policy gradient, it represents policy as the action probabilities at a state. Combining these two, we get actor-critic methods. The critic gives comments on the actor's job and leads actor to better performance. We use actor-critic to solve our problem, and if we use deep neural network to decide the agent's behavior, we get deep reinforcement learning. This page shows us the general principle of the approach. The previous optimization problem can be solved by column generation, CG in brief, which finds the acceptable patterns in pricing problem and updates the master problem with the new patterns and gets the scheduling strategy eventually. We use the pricing problem in CG to produce candidate patterns as the input to the RL. We choose actor-critic method as the RL learning algorithm that decides which action to be executed. And we compare the scheduling results from the master problem in CG, which is actually a general approach against the RL solutions. We first formulate the optimization problem as a buckets pipes game RL plays with. Exactly, donor acts as a very big tank which always contains water. The IAB nodes and the users are regarded as some buckets, the green and little wooden ones in the picture. The data bits are just like the water. The links are the pipes, each of which has a valve to control its availability. Some pipes can get clogged, which is similar to the link blockages. A link pattern is actually a set of valves that can be opened together. The valves that the 5 hands pointed at are defined by the links of a pattern, and they're selected to be opened in the current slot. We can see that if the upstream buckets have water and the pipes are not clogged, the water can flow to the downstream buckets. Based on the buckets pipes game formulation, we design the state, action, and reward. To simply put, the state is composed of the normalized number of bits on the IAB nodes, and actions are the patterns. The reward, if not all the pipes in a pattern can transfer water in a slot, we assign a negative value to the reward for that action. Otherwise, we set reward as the number of access pipes You can find more details in the paper. Then we show some experimental results. The setups for network scenarios are as follows here. We test on 10 instances, each of which includes 4 IAB nodes and 30 users, considering MCS 16 and 8 for backhaul and access. This is an example layout of the network instance. We compare the proposed DRL-based approach with quasi-optimal reference CG and the random pattern selection strategy. The table here shows some neural network settings for offline and online schemes, including layers and units, learning rate, and batch size. We first analyzed the performance of the offline scheme from the perspective of UE data rate CDF. We train a neural network model which defines the agent behavior with the realistic instances of the random environment and then apply it in real-time tests. Here are the results with the blockage probability 0, 0.2, and 0.8. We can see DRL-based and CG can reach the data rate limit of MCS 8. And DRL's performance can approximate CG in non-blocked case. When the probability is raised to 0.8, it outperforms the CG here. Then we evaluate the offline scheme using traffic volumes. We can see that for all the 3 methods, the number of data bits transferred to UEs decrease as the probability is increased. DRL surpasses CG opt when the blockage probability is raised to 0.8. We can see the difference here. As for the online scheme, we apply and train a model in parallel so we can capture the dynamics on the fly. In the experiments, initially, we have 4 links to be blocked with probability 0.8, and then we keep the probability and first block another 4 bottleneck links, and later block another 4 non-bottleneck links. These 2 figures show episode reward and the equivalent of the user throughput. We see that the offline scheme's throughput plummets remarkably at both changes, here and here. On the opposite, the online scheme also sees a drop at the first change, but immediately goes up and doesn't see any decrease at the second change. Exploration branches in online scheme may lead to the performance oscillations, but overall performance is better compared to the offline scheme. Coming to the conclusions of this talk, we propose a DRL-based flow allocation and link scheduling approach for mmWave IAB networks, including both an offline scheme and an online scheme. We put more emphasis on dealing with the dynamic changes of the environment and rapidly recover from the performance decrease, which is demonstrated to outperform the classical optimization methods. We are working on the extensions of this work, considering the issues like other blockage models and some correlations among link failures. Thanks for your attention. Hope to see you in the online discussion. I'm glad to answer your questions.